All right, welcome back, everyone. In this session, what we're going to talk about is the idea of heat treatment. And really, what heat treatment is it's a way to change the fundamental properties and characteristics of metals through, as the definition says, by heating them up and then cooling them. And based on how hot you heat your metal, how quickly you let it cool, and the method you let it cool, it can change these properties. So let's start with the definition of heat treatment. So, like I just said, what we're talking about is a process used to alter the properties and characteristics of metals by heating and cooling. So there's really three steps or three stages to this process. So let's jot down those three stages. The first is that we need to heat our metal, and we're going to heat it to some predetermined temperature. And I'm sure you can imagine that if you were less than that temperature, that would have some characteristics, versus if you were to overheat it, in essence, you could turn it into a molten lava, right? So there is some desired range, and the properties will depend a little bit on that range, which we'll get to in just a little bit. The second step in this process is once you're at that temperature, you want to keep it at that temperature for a required amount of time. And the reason you're doing that, and once again, we'll talk about this in a little bit, but while you're at the temperature, things are going on within the metal, and we need to have that process happen for a certain amount of time, like 45 minutes or something. So, as it says here, keep it at that temperature for this required amount of time, and after that we need to cool it. Now, that is, the material properties will be somewhat determined on how fast that rate of cooling happens. So that's basically the process, and I put in here for the desired properties, like I said, depending on how fast you cool it, it'll change the characteristics of your metal. So before we really get into it, there's a lot of new terminology here, and you don't want to get too tight in the terminology, so I thought it would be easier to try and, in essence, make a short definition of these terms before we actually talk about the process of heat treatment. So the terminology starts with this idea of pearlite. And what pearlite is basically steel in its natural state. Nothing's been done to it. So this is what we're considering our non-hardened steel or natural state. Okay, a second term that we should be familiar with is decalescence. And I did go from numbering them to bullets. Hopefully that didn't screw you up, but numbering didn't seem to make much sense. So the easiest way to talk about decalescence is if we were to think about phase changes in a common material like water. So hopefully you remember or you're familiar with phase changes, meaning if I have a temperature and I'm adding heat, and say we have water, then it goes up, and basically, actually starting with ice, let's go all the way back to ice. If I heat up ice, it can get warmer and warmer until I reach this melting point, right? And once I reach the melting point, then we're flat, meaning I'm adding more and more heat to it, but it's still this ice water, and ice water will remain at the same temperature, 0 degrees Celsius or 32 Fahrenheit, until it is 100% water. Once it's 100% water, after the phase change, then I can increase the temperature again until it starts to boil, right? And hopefully remember that while it's boiling, then we aren't actually changing temperature. It's the same temperature boiling, well, even though I'm adding in this extra heat. So this temperature here is similar with this decalescence term, meaning if we were to heat up steel, it gets warmer and warmer and warmer, and then it gets to this point where you're still adding heat, but the temperature is not changing. And it's similar to a phase change, is what's going on at the molecular level as everything's changing. So if I had to put that in words for decalescence, I would write down something like similar to a phase change between liquid and gas, temperature is stable as we add more heat. Another term we should be familiar with is austenite. And we're going to look at this heating up process in just a second, but just so you can get familiar with the word, the definition that I'd say is this is similar, like we said, with this Decalescence is the point where there's like a phase change. So when we talk about austenite, what that is the phase when we are above that decalescence point, but below a critical point, which would be like the absolute maximum that we're looking at. All right, so other than austenite, very similar to decalescence is going to be a term that we should know. It's called recolescence. And recolescence is pretty much the same thing as decalescence. The only difference is it's during the cooling process as opposed to the heating process. So it's almost like a phase change going in reverse. And then the last term that I want to go over before we draw this little phase thing is our martensite. So we talked about pearlite, and that was the non-hardened steel, its natural state. Well, martensite is the hardened state of steel. And basically this comes about from cooling it very quickly, and we cool it so quickly that we skip the recolescence point and go right into almost like skipping that whole phase. And what this does is it causes extra stresses in the steel, and it makes it more brittle, but it makes it harder. So there's some property values here about making the steel harder but more brittle. All right, so now that we have those terms out of the way, let's take a quick look at what's actually going on here during this heating and cooling process. If I were to set up a graph, and on my vertical axis I'm going to have my temperature, and on my horizontal axis I'm going to have time. What we can do is start heating our steel, and just like we just saw in a phase diagram for any other material, what we would have is a linear relationship. Meaning the more I heat it, then the more energy I add to it, then the higher the temperature. And this happens up to a certain point, which we kind of described a second ago. And that point is roughly 1330 degrees Fahrenheit. And that is our point of decalescence. And after we do that, then our steel continues to absorb energy, but it doesn't increase in temperature until this process is basically complete. And then after that process is complete, then it'll start going up again as it absorbs more of this energy and increases temperature and hits a peak value and then comes back down. Now this peak value is somewhat variable, depends on the amount of carbon in this steel in the beginning. However, we're going to put it here just so we can talk about it, 1600 degrees Fahrenheit. And I will put a little note on here that what this value is, at least right now, is it's an approximate value and depends on your carbon content. As we are working back down, and this is basically like cooling, so after we get to this critical point, this 1600 degrees Fahrenheit, we remove our heat and our metal starts to cool back down, and this will happen until we get to about 1300 degrees Fahrenheit, so slightly less than our decalescence point, and that will be our recolescence point. And then after that phase is complete, then cools back down to where we started from. So we said there's this term that we defined earlier of pearlite, and that was the non-hardened steel, its natural state. So we're starting, if you think about it, over here in this pearlite state, right? Everything over here or below that point, and same thing over here. So this is where we are in this pearlite state. Now there's this other, once we get up to that phase change, or right above our decalescence point, what we've moved into is a new state, and that state is our austenite. Remember when I said that was the phase when steel is above the decalescence point but below critical? So that is up here. So of course you could think of it being on either side. Hopefully that makes sense. It's basically, it's this whole area, you know, like in here, but technically it's a little lower on that side. It's not really a great graph for showing that, but it's anywhere after this decalescence until I get all the way back down to my recolescence. All that is considered that austenite state for that steel. So that would be the general process if I heated up a steel past that decalescence point and then let it cool back down. What we are doing is we are in essence with this idea of heat treatment is we're hijacking this process. And the way it works is we are going to heat up our steel, so we're moving along this graph, we get to that decalescence, and then remember up here for the phases where it says we need to keep it at that temperature for a required amount of time. Well, the reason it's a required amount of time is what we're doing is we're working right along this flat section, right? So that's our required time to get all the molecules, the molecular level, to start to line up in their certain way, and then we start to move up while we're in this austenite phase. Now, if we were to suddenly cool it, quench it, dump it in a bucket of cold water, what happens is we have a very quick cooling off period, and it looks like that. And so I'm going to call this quench. It's the instantaneous cooling. Now, if we quench it, we can get back to that original room temperature, but what we missed, the recolescence stage, right? We don't have that flat where at the molecular level things are going back to normal. So we basically froze it in place. And what this is this is now where we're talking about a hardened steel. And like in our definitions, we said state-wise, this is the martensite state, or also known as hardened steel. Now, it's great that it's harder because that means it's more resistant to wear, right? Unfortunately, there's some other characteristics that happen when we go through this process. What really happens is we are increasing the stresses within the metal, right? Because all of our particles or all our molecules are trying to move back around, and we have these extra stresses. And it makes the steel very brittle. And that means it's susceptible to cracking or fracturing, because like we talked about before, steel in general is very ductile, meaning I can bend steel and it'll just bend. Well, if it were heat treated, if I were trying to do that, it would just snap, right? That's the brittle part of steel. And that's what we have done with this process. So there are some things that we can do to it to help regulate that idea of being overly brittle. One of them is this idea of tempering the steel, or tempered. And what tempering does is it reduces those internal stresses to some extent, not all the way, but reduces it somewhat, and it therefore will reduce that brittleness and the susceptibility of cracking. Now, the process to do that is after we have this hardened steel, meaning we have, see if I can draw right on top of this, we've heated it, we've gotten to that decalescence, we've waited till that process was complete, and we started going up, and then suddenly we quench it and we're down here. After that process, what we can do is take that steel and heat it up again. In the second heating, we aren't going to go as all the way up to the decalescence. In fact, we're going to go about half that, to about 600 degrees Fahrenheit. So we'll just go up to like this phase, right? To like 600 or so. And once we heat it to that level, then we allow it to cool naturally. Well, if it's cooling naturally, basically if you can think of all of these molecules frozen in place, and then we've heated it up so it lets them flow just a little bit, not all the way up to the decalescence, but a little bit, and then we're letting it cool naturally so that they can release some of those stresses. So you'd have something that goes like this, and there'd be something like that, right? So let me write down the process in order to temper it. So that's what a tempered steel would go through. As an option, what we could also do is we could increase the temperature more up past that decalescence point. And if we were to go up past that decalescence point and then let it cool naturally. Now, when I say past the decalescence, this is for that martensite, right? And then if we let it cool, you can imagine now we're going down and we are letting all of this kind of come back. And this is where we end up with a much softer metal. We've removed a lot of the stresses. It's much more pliable. And this process is called annealing. And of course, you can imagine that it is somewhat time dependent. So the longer we're on our little horizontal segment here, the more of the it's almost like reversing the process, right? The more we will reverse the process of the heat treatment. All right, so let's talk about the process of annealing, even though I just drew it there. So now, like I said, we are going to heat our martensite past our decollescence point, and then we're going to let it cool naturally. And if we let it cool naturally, then basically we're bringing it back to that pearlite state. So the last term we need to talk about is it's annealing, but that annealing that we just talked about was starting off with a piece of metal that's in the martensite state. What if we were to do it with a piece of pearlite? So we're in our natural state, we heat it up all the way past that decollescence point, and then we let it cool naturally. What this is called is normalizing. So jotting down a quick definition, this is the same idea of annealing, but in this case we're going to say that it had never gone through that heat treatment process or that hardening state. So as a quick little review, as far as the heat treatment process, what we're doing is we're heating our metal past this particular point, this decollescence point. We're letting it sit there for a period of time while all these molecules are reforming. Then after we get up and we're starting to increase our temperature a little bit more, we quench it. And when we quench it, now we have a much harder yet brittle material. And because it is brittle, what we can do is we can temper it. And the way we temper is we heat it back up, but not as high, about 600 degrees Fahrenheit, and then let that cool naturally, freeing up some of this binding of the molecules. And then there's some other processes we can do, such as annealing, which is bringing it all the way up to the decollescence point and then letting it come back to its natural state. Or we can normalize, which is the annealing process with our unhardened material. So hopefully that was somewhat informative on the topic of heat treatment. Feel free to read the book. The chapter is very in-depth on heat treatment. It goes into much more on the molecular level and a little more detail. I tried to keep it somewhat simple just to get to the basics. Of course, this is all you'll be required for this class, but if you want more detail, feel free to hit up the book, and we hopefully will be able to do a lab that'll reinforce this heat treatment process as well. So that's what I have. Good luck, and I'll see you all next time. Thanks.